All right, I got glasses to look smart. Let me see how I look actually. They do nothing, by the way. I'm just ahead of the curve. Have you seen the guy who says ahead of the sexuals? They're talking about homosexuals, and he thinks that the word is ahead of the sexuals. It's funny, but whatever. We got 3.5. Counting subsets. What the fuck? Haven't I already gone through this? What is a power set again? Isn't that basically counting subsets? Whatever. The previous sections dealt with counting lists made by selecting k entries from a set of n elements. We turn now to a related question. Yes, obviously we've been through it. Right? How many subsets can be made by selecting k elements from a set with n elements? I feel I'm familiar with this, shouldn't I be? Sometimes the clear definitions, or like the distinctions, I guess, between similar looking, similar feeling, similar I concepts is tricky. But once you see the differences, you will definitely learn something. Actually, the more differences you see, the more parts you can break something up in. The I mean, it's gonna get harder, and it's probably gonna require more. But you know, the more accurate picture you can get of any idea. So that's why I hate today's debates. You know what? No, I'm not gonna get into it. Whatever. To see the difference between these two problems, take A. Let's write it up. So we have A, which is a set. We have some elements. How many do we have? 5. So we got A, B, C, D, E, right? Now, consider the non-repetitive lists made from selecting 2 elements from A, only 2. Fact 3.4, which I do not remember what fact that is, but it says that, all right, so this is basically permutations, right? We got P, 5.2, and that would give us 20, correct? 5.2? Shoo, you foggy me! Wouldn't it be? This is permutations, baby. This is permutations, baby. Shouldn't this be actually? Where's the where's the 3? Wait a minute. Something's. See, now we're getting into something that I don't quite. Maybe I haven't seen this because they're saying that this should be 5 times 4, which obviously is 20. But then for the permutations, wouldn't it be this? And then what am I doing here? This is my instinct to write this. Why? Because this would be 5 times 4 times 3. Am I missing out on something? Have I forgotten something? Which happens, once you stop doing it every day. But all right, I am fairly certain that P parentheses 5.2 comma 2 would be a permutation. So, and then it would be, oh, wait. It would actually be 5 minus 2, which would be 3 factorial. Yes. What's the difference? Why is it this way? This should be obvious. And yet, when I remembered it just now, it wasn't. So that's a hole in my understanding that I have now identified. So let's go back to basics. What is a permutation really? It's how many, well, it's this. How many parts of a set can you pick out? And then how many combinations of these two parts would you be able to make? Right? And it's basically counting. That's the chapter we're on. Yes, yes, yes. What else we got? Why wouldn't it be 2 factorial? Because with 2 factorial, I would have removed. No, why wouldn't it be 2 factorial? Hmm. Interesting. Something's fucked. See, I'm not getting too far. But this is kind of how you discover weaknesses. And this clearly is a weakness because I would think that if you're picking out two, logically, if you picked out three, well, oh yeah, if I picked out three, I would remove even more from the solution than if I picked out two. Now that doesn't make sense already, but then how would I explain it accurately? What does it do? To Oh, right, because hold up, just a factorial, right? That would be an ordered list of like combinations if you picked out every element. Now you're gonna have to pick out every element as you do with 5 factorial, but then you have to remove all the orders of the elements you didn't pick out, which would be 3 factorial. Yes, obviously. Quite elementary, my dear boy. Sometimes, you get these. Yeah. All right. Now it makes sense. I will probably remember it even better. See, it's not enough to just solve assignments. It's not enough to just read through the course. I would be able to probably, like, if I had a test and I did it, which, by the way, when you have a test, you don't really have time for all this bullshit that I'm doing right now. But I do believe that you learn a lot more when you're like just honest about it. Maybe it's obvious. For me, it wasn't always. And maybe for a lot of people, well, I've seen, for a lot of people, it's not obvious. Especially in mathematics. It's a real special subject which requires full engagement. Engage. You know? So here we go. They list up, but there are only. Wait a minute. So they list up all the 20 possibilities, could you call it? But they say there are only 10 two element subsets of A. Subsets of A. Why? All right, let's go on. The reason that there are more lists than subsets is that changing the order of entries of a list produces a different. Yeah, obviously. All right. So now I was just blind to the differences between a list and a set. So what are we doing here, really? Let me go back, actually. The previous. All right. So now we're doing subsets instead of lists. Yes, 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 yes. Same page, same page. And then let's see. Yeah, so the order matters, right? In a list, in a set, it really doesn't. And using elements, let's see. We use the elements AB of A, big A, big A, boop, boop. We can make two lists, AB and BA, but only one subset, AB or BA. But that's the same subset. And then this section is concerned with counting subsets, not lists. Basically, we're saying that the order, the thing that we're trying to count, we don't give a fuck about the order. Okay? So, yes, interesting how many subsets can be made by choosing k elements from an n element set. Obviously, we're not able to just use permutations because they are concerned with orders, so I would figure out that it would be combinations? No, wait. Yeah, right? Am I tripping? Well, whatever. Notation that gives name to the answer to this question. So let's just write up a definition, right? Definition 3.2. So if n and k are integers, interesting, then this denotes the number of subsets that can be made by choosing k elements. I'm not gonna, you know what, probably I shouldn't write it. That can be made choosing k elements from an n element set. We read n choose k as n choose k. Some textbooks write c nk instead of nk in parentheses like this. And I would figure that the C stands for combinations. That's like a little clue that I might have been right. You know, I'm not like, I'm weak at this stuff, but it doesn't matter. This is illustrated in the following table that tallies the k element subsets of the 4-element set. So there's a set. There's a set A. And it has 4 elements, A, B, C, D. Here we go. And let's see. So they tally up, tally ho, for various values of k. Now, so they choose, all right, so they include like a -1, -1 k. That would give us 0. 0k would give us 1. That would give us the empty set. Now, interestingly enough, for whatever reason, and this I'm going to grab onto a little bit, why is the empty set not included in the 10 2-element subset of A that we talked about previously? There are 10 subsets here. I don't see the empty set anywhere. And yet, when you choose 0 elements, you get 1. The subset now is included. Similarly, down here, they choose 1, 4 subsets. Choose 2, 6 subsets, right? And once you go beyond, like if you choose more elements than you have, you go back to 0. But 0 exactly, why does that give us 1 subset? Are we back to screwing around with the factorial? Because there's something here that doesn't quite caress me as gently that I would like it to do. The values of k appear. Do they just gloss by it? Let's see. The values of k, and they're just explaining the table. Whatever. Blah, 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 blah. Yeah. So when k equals 0, there is only one subset of A that has cardinality k. Cardinality is basically, I guess, the size of the set. No, wait, how many elements are in it? I think would be, because it would not make it's. We're not doing physics, all right? So let's not think about size right now. Is that even correct? Well, whatever. So it has cardinality k. The empty set. So k is directly related to the cardinality. It doesn't mean that we're choosing, or does it? Now, this kind of, there's something here that I'm not quite, but yeah. All right. It kind of makes it a little bit more clear, but there's still something, cardinality, k. So why don't we include, still though, why don't we include the empty set in all the other cardinalities here? Of course, because once the cardinality is 1, it can't be 0. Why would you include that? It's cardinality, really, that we're worried about, right? Not just, it's all cardinality. It's all cardinality, always has been. Yeah, I'm a meme lord, don't worry about it. So yeah, all right, so that makes sense. Notice that if k is negative or greater than the cardinality of the set you're talking about, then then A has no subsets of cardinality k, and then we get 0 subsets in those cases. So, and then they get some general stuff, but it kind of makes sense. I don't think I would derive this a general statement from the understanding that I have, so I'm not too worried about that. About that. Catch me outside. How about that? Although it was not hard to work out the values of for choose k by writing out subsets in the above table, this method is actually listing sets of of actually listing sets would not be practical for computing n choose k when n and k are large. Yeah, so we need a formula. We need a formula. We need a formula, my boy. To find one, we will now carefully work out the value of 5 choose 3 in a way that highlights a pattern that points the way to a formula. I just don't like pointing. You know, I really appreciate when people, but I know it's not realistic. I get it, but I appreciate when people like see the image, and but that's how I do it a lot of the times too. Whatever. But I'm not that smart. You know what I'm saying? So I'm like expecting. But then whatever. We need a formula. All right. So let's point the way. Then they go around and say stuff like, to begin, note that 5 choose 3 is the number of 3-element subsets of A, B, C, D, E. A set with cardinality of 5, you know? I mean, it has 5 elements is what I'm trying to say. And then we choose 3, obviously, from the stuff that I said earlier. The column under each subset tallies the 3 factorial, 6 permutations of that subset. The first subset, ABC, has, what the fuck just happened? Has 3 factorial equals 6 permutations. These are listed below it. Oh, so this is what they're doing. They're setting up basically like a table. Horizontally, they list up all the subsets, and then they have a table of all the lists of 3 factorial. The body of this table has 5 choose 3 columns in 3 factorial rows. This might be a little bit, I'm not sure where they're going with it, but is this going to be numerical? No. Because it would be cool to just like now go through down the, each cell and like just booleanly say if this is the same as the one in the possible subsets we have, and then just remove all the lists that do not. But then that would not help us do a formula, so that's like stupid, I guess. Notice that the list consists of every 3 permutations of A, B, C, D, E. And then we have like a fact about the permutations of 5.3. 5 choose 3. Would you still say that? I mean, yes, it's the same thing. 5 choose 3. It's just different notation. It confused me for a little while, but it doesn't matter. The total number of lists in the table can be written as either 3 factorial times 5 choose 3. I was almost there. That's how we do it. Or, and then there would be or 5 factorial divided by 5 minus 3 factorial, but that's the same as 5 choose 3. And where did the 3 factorial go? Wait, what the goddamn hell? Wait, permutations and choosing, is that not the same thing then? That's what I've been thinking. Are you telling me that now this would not be the same as this? So what is this notation on the right? Is that the subset one where we care about order? But don't we care about order in permutations as well? I'm sorry, that we don't care about order. Yeah, actually, yeah, on the right here. See, I've done probability way too. I mean, counting. Not that much. All right, doesn't matter. I'm getting defensive a little bit, but it's okay. We're allowed to be stupid, aren't we? As long as we keep evolving. Working this out, you will find out that it gives the correct value of 10. And because... But now something's fucking me up a little bit. Because they're saying now that 3 factorial, 5 choose 3, would be exactly the same as 5 factorial, and then 2 factorial. Oh, well, let me write it like 5 minus 3 factorial, right? How did they get here? How did they get here? How do I reach the kids? Um, because maybe. All right, let me go back. So the columns are obviously 5 choose 3, which are the subsets that we're talking about. Um, Wait, didn't I see here that actually, yes, because yeah. All right, so they used a small number of examples just to be able to manually, without any formula, figure it out. And then here they have some more elements that they are choosing from the set, but still enough to make a whole fucking table out of them. Now we have 3 factorial of rows, so I'm not gonna write it, but they have like a table, and they do this. So this would be 3 factorial, and then they have a kind of like a horizontal list or whatever of 5 choose 3. Now, why do this? I figured they want to somehow tell me that the full list combined would be because you can't really multiply, can you? Anyway, all right, so we can write it 3 factorial times 5 choose 3, which I do not fucking get. The total number of lists in the table can be written as 3 factorial times like this stuff. How the fuck can you say that? You want to have like a finite calculation, like kind of like, let's say, a geometrical area, and that's what it seems like to me. They're like, bear with me, all right? Like, this is just how my mind is thinking about it. You want to count how many lists you got there? All you're doing is like, because I'm thinking it's probably wrong. You're like, what, multiplying the height times the width? That's where they're pointing me at this point. And that doesn't make any sense because the height here wouldn't be 3 factorial. Actually, the whole fucking table down here would be 3 factorial. All the elements in there. So what do you mean that the total number of lists in the table, and by the way, which table are you talking about? Just this one or this one? Because technically this could be a table as well, right? Can be written as either 3 factorial times 5 choose 3 or 5 factorial divided by essentially 2 factorial. So they're saying they're the same thing. And basically, all right, let's go a little further. They're saying that, all right, so you divide 3 factorial. Basically, you end up on this. Let's see where we end up and see if we can work our way back to figuring out. So we get this, right? Which I've clearly seen. Well, not clearly, because I'm fucking this up. So for me, I have clearly seen this before, and this will basically um, dismiss the order. We don't care about order here. And then they go ahead and generalize it. However, there's still what is with this table, my guy? What is with this table that they're doing here? It has a table. No, it has a total. See, they say the body of this table has 5 choose 3 columns and 3 factorial rows. So it has a total of 3 factorial times 5 choose 3 lists. However, I don't see that it has 3 factorial rows. I'm sorry, go fuck yourself, because rows, they go like this. And 3 factorial, it gives you every list. And then in every row, there are multiple lists. So there can't be as many rows as there are lists, because there are more lists than there are rows. So what the fuck are they trying to pull on me right here? What am I not seeing? Never assume that the book is wrong, although it sometimes is, but always assume you're wrong first, which I always am, almost. No, it clearly says 3 factorial rows. But that's just not true, is it? Now, if they were to say, every 3 permutations of A, B, C, D. Oh, wait. So that is actually... Now, wait a minute. The table consists of every 3 permutations of A, B, C, D, E. Right. Now, now this one I would get that every 3 permutations would basically be 5 factorial over 2 factorial, right, permutations. But then to say that the table can be written as 3 factorial times 5 choose 3, I don't see that connection. I don't see that jump. I really don't, you know? And why not? Maybe I'm looking at it all wrong, because I'm trying to I'm seeing the height of the table, the width, and I see that they multiply those. But what are they actually trying to count? They're trying to count the lists in the table. But why are they setting it up this way? There must be some reason for it. I need to take a piss. Jesus, I just went to the bathroom and then I got down a rabbit hole on fucking Instagram with this whole social media ban for people who are less than 16. And then people are like, oh, this is going to lead to digital ID checks and all that stuff. Actually, I don't think you should be anonymous online. Then again, I don't trust necessarily the people in power. So I don't know what to do about this. Let's just do some mathematics, and it's not going to work itself out, but yeah, fuck it. Whatever. So this is, if we get smarter, maybe that'll help. So let's try to do that. All right. So where did I end up? Oh yeah, I don't get the table. I don't understand how this is actually 3 factorials. I don't understand how the total number of lists in the table can be written as 3 factorial times 5 choose 3. Now 5 choose 3, see, I think the essence is that in my mind 3 factorial would be all the lists in the table, but it wouldn't be, obviously. 3 factorial is just 6. 1, 2, 3, 4, 5, 6. Yes, that would be the height. Oh, goddamn! Now I see it. Why did I think that the whole list would be 3 factorial? That's an interesting. That's we're let's finger that one a little bit. Whoop, can you say that? I don't know. Let's look at it because we have ABC. Yeah, yeah, yeah. So we have 3 elements and we just fucking permutate those. We get 6. Yeah. So that would be the rows. And we have those rows. Then yes, you would get actually obviously the total number of lists. Yes. Yes, yes, yes. But why did I think that the full list? What do I think the full list here is? The full list would be, how would I even calculate the full list? Right? Now the full list would not care about would care about order, so that would be just a permutation. So now if I were to calculate the full list, that would be, yes, 5 factorial divided by 2 factorial, and also it all clicks into place. This is good. This is great. All right, so now we have a definition for n choose k, and it's actually, now no order is what do you say? Order doesn't matter. So n factorial divided by k factorial times n minus k factorial. Makes sense. And then we got some few. All right, whatever. Now we got, so how many size 4 subsets does 1, 2, 3, 4, 5, 6, 7, 8, 9 have? The answer is, oh, and they just kind of use this rule a bunch of times. Actually, I'm not sure if we should go through all of these. I don't think it's necessary. They're just kind of using this in practice. Let's just go straight to the exercises. Why don't we? And that's going to be a video on its own.